Okay, so why is formal charge a source of reactivity? Question. Why a source of reactivity? Why are we even looking at this? Okay, and let me answer this question by asking you another question. Hey, you guys, in our last session, what did we say was favored in chemistry? Stability or instability? Stability, right? Was the marker more stable standing up in my hand or lying down? Lying down, right? And since it was more stable lying down, we said that lying down was favored. Stability is always favored over instability. Remember the relationship, you guys? High stability equals low energy equals low reactivity. Low stability equals high energy equals high reactivity. In a reaction, things always go from unstable to stable. So, hey you guys, how does this relate to formal charge? Well, let me just tell you that charges are very, very unstable. If an atom has a formal charge on it, and by formal charge I mean a full positive or a full negative charge, then that atom is going to do whatever it can to get rid of it. It's going to react. It's going to make bonds or break bonds to try to get rid of that charge, because the goal of all atoms is to be neutral. All atoms want to be stable, right? A neutral atom is a stable atom, which also makes it low in energy and low reactivity. A positively or negatively charged atom is an unstable atom. A charge is very unstable, making it high in energy and high in reactivity. An atom with a charge on it is going to react, okay? So if there's one thing I want you to take from this section, is that whenever you see a full positive or a full negative charge on an atom, like hey, when we saw H3O plus, we saw a plus charge on that oxygen, or when we saw OH minus, we saw a minus charge on that oxygen. Whenever you see a full positive or a full negative charge on an atom, you better believe that something is going to happen there. A reaction is going to happen there. That atom is going to make or break a bond in order to get rid of that charge and become neutral, right? In this case, oxygen wants to break this bond so that it can get 1, 2, 3, 4, 5, 6 valence electrons around it to become neutral. In this case, this oxygen wants to make another bond so that it can have 1, 2, 3, 4, 5, 6 total valence electrons directly around it to become neutral, right? So hey, whenever you see a positive or negative formal charge, it should scream out at you, hey, a reaction is going to happen at this atom, right? And that is why being able to find formal charge is so important, because it shows you where a reaction is going to occur. It's going to take place, right? So in answer to this question, why is it a source of reactivity? Well, the answer is because all atoms want to be neutral. Because all atoms want to be neutral. Okay, so subsequently, since all atoms want to be neutral, then these atoms are therefore going to react. They're going to make bonds or break bonds to become neutral. Okay, you guys? And hey, if you ever hear me saying that an atom doesn't have a formal charge on it, that's just another way of saying that it has a formal charge of 0, okay? And if it has a formal charge of 0, that means it's neutral and not likely to react, okay? Just in case that was confusing some of you. Alright, so hey, the first way to check for reactivity is by checking formal charges on atoms, checking whether atoms have full positive or full negative charges on them. But hey, if you don't see any full positive or full negative charges on atoms, the next best thing to look for is partial positive or partial negative charges on atoms. Because hey, partial charges are another great source of reactivity, and you'll see these everywhere when dealing with polar covalent compounds, okay? So hey, let's take a look at this. Okay, so the second source of reactivity, I'm going to call this partial charges, or partial charge. Partial charge. And really there's not too much to explain conceptually here because it's a similar concept to formal charge. Except with formal charge we were talking about full positive and full negative charges. Here we're talking about partial negative and partial positive charges. But hey, it's the same concept. Atoms with partial charges on them feel the exact same way as atoms with full charges on them. They want to be neutral too, right? And even though having a partial charge isn't as bad, isn't as unstable as having a full charge, these atoms still want to do whatever they can to become neutral. And so they also make and break bonds to try to cancel out the charge, okay? So, hey, let me ask you a quick question. If we were saying that these atoms with partial charges aren't as unstable as atoms with full charges, then would you say that a partial charge is more or less reactive than a full charge? A partial charge is actually less reactive than a full charge, right you guys? Because if it's more stable than a full charge, that means it's lower in energy and therefore less reactive. So, hey, this might seem like kind of a weird concept, you guys, because we're saying that a partial charge is unstable. It is reactive still, but just not as unstable, not as reactive as a full charge, okay? And this is why I'm telling you to look for partial charges second and formal charges first. Formal charges are the most obvious source of reactivity. Atoms with full charges are the most reactive. Partial charges are the second thing to check for because, hey, they're less reactive. They're still reactive, but they're less reactive than full charges, okay? So, hey, here's just a quick example of how to look for partial charges. So, hey, let's take, for example, HCl. Okay, so whenever you're looking for a partial charge in a compound, what you're actually looking for is whether one atom is more electronegative than another atom. So, hey you guys, in HCl, hydrochloric acid, is there one atom that's more electronegative than another atom? Is there one atom that's pulling electrons closer to itself away from the other atom? Yeah? The chlorine, right you guys? The chlorine is pulling electrons closer to itself away from the hydrogen. And we know that this is the case because chlorine has a higher electronegativity than hydrogen, right? And hey you guys, are electrons positively, negatively, or neutrally charged? Negatively charged, right? So hey, if chlorine is pulling electrons towards itself and electrons are negatively charged, then would you say that chlorine is becoming more negative, more positive, or staying the same? More negative, right you guys? So we'd say that chlorine is partially negative and we'd indicate that by writing the delta negative sign next to it. Delta minus. Okay? And this indicates that it's becoming partially negative when it's pulling electrons towards itself. Okay, so hey, keep in mind you guys, chlorine isn't completely taking electrons away from hydrogen. It's still sharing electrons with hydrogen. So hey, that's why we say it has a partial negative charge and not a full negative charge, okay? Because they're still sharing those electrons. All right, so now let's look at hydrogen. If hydrogen is less electronegative than chlorine, meaning that it's getting its electrons pulled away from it, then when you say that the hydrogen is becoming more negative, more positive, or staying the same? Okay, well if negatively charged electrons are being pulled away from the hydrogen, then would that mean it's becoming less negative? Or another way of saying less negative is becoming more positive? And yes, this is the case. Hydrogen is partially positive. So we'd indicate that by writing a delta positive next to it. And just to be thorough, you guys, is this a polar covalent bond? Yeah, it is, right? Because electrons are being shared unequally, right, you guys? And when you share electrons unequally, you create two poles, a positive pole and a negative pole, right, you guys? And so to be complete, why don't we draw a dipole arrow? And the arrow always points towards the more electronegative atom, and the vertical crosshatch goes to the atom that's having its electrons pulled away from it, all right? Okay, so hey, remember the arrow points in the direction of the more electronegative atom, the chlorine. It's pointing the way the electrons are being pulled. So hey, you guys, in this case, the arrow points to chlorine, indicating that it's partially negative. And hey, don't forget the vertical crosshatch next to the hydrogen, indicating that it's partially positive, right? Okay, so that's how you look for partial positive and partial negative charges. You'll see later how these work in actual reactions, but for now I just want you to be able to identify them and realize that a reaction might happen at these partial charges. The main thing that we're doing right now, you guys, is laying the foundation for you to learn chemical reactions. I'm teaching you guys how to look for reactivity right now so that when you're learning reactions later, you won't just see what is happening, but why it's happening that way, okay? Okay, so let's get to the third source of reactivity. All right, so the third source of reactivity, I'm going to call this functional groups. So number 3, this is functional groups. Functional groups. And there are 9 main functional groups you guys are going to be learning. Does anyone know what a functional group is? Okay, well, a functional group is just a site of reactivity that always reacts the same way. Let's write that down. A functional group is equal to a site of reactivity that always reacts the same. Okay, so what this means is that any compound that belongs to a specific functional group will react the exact same way as any other compound in that same functional group. The point is that there are groups of compounds in chemistry that react in characteristic ways in every situation. And this is a really powerful thing to understand because, hey, once you know how one compound of a functional group reacts, you know how every single compound in that functional group will react. And hey, if you don't understand this now, you will later in the course because you don't want to learn 100 specific reactions. You want to learn a couple general reactions and apply that knowledge to specific reactions, okay? But anyways, let's write down these functional groups you guys need to know, okay?